Welcome to This Explainer. Today, we're taking a perfectly ordinary object and pushing it to the absolute physics-breaking limits of the universe. We're going to dive into an absurd, entirely hypothetical, and honestly kind of terrifying thought experiment, one that starts with a tiny piece of household metal and ends with the complete restructuring of our solar system. So here's the central question, the exact one whispered in quiet physics rooms when scientists want to test the extreme bleeding edges of their equations. What happens if a standard 0.1 gram sewing needle strikes our planet while traveling at a significant fraction of the speed of light? Well, spoiler alert, the answer isn't just a tiny crater. As we escalate the speed, rung by rung, the stakes grow from localized damage to the literal unbinding of a world. Let's really break down the core paradox here. On one hand, you've got the physical mass of a tiny needle. It's practically nothing, right? Drop it and it barely dents a wooden floor. But on the other side, you've got an energy yield measured in millions of megatons. Because at these insane relativistic speeds, the physical mass of the needle is totally irrelevant. The needle isn't even an object anymore. It's literally just a delivery mechanism for pure, unadulterated kinetic energy. Now, to understand how a sewing needle can actually destroy a planet, we have to look at the mathematical engine driving the destruction, the Lorentz factor, or gamma. As an object accelerates closer and closer to the speed of light, this multiplier causes its kinetic energy to grow exponentially, without bound, meaning every single time we tack on another 9 to the needle's speed, like going from 0.99 to 0.999 times the speed of light, we are drastically multiplying the danger. So let's map out the first few rungs of what we like to call the extinction ladder. At just 0.9 times the speed of light, the needle hits with 2.8 kilotons of force. That's twice the yield of the Hiroshima bomb from a piece of metal the size of a toothpick. Add 2 more 9s, 0.999, and we're up to 46 kilotons. The atmosphere essentially turns into a particle accelerator, creating a massive nuclear airburst and a shockwave that would strip the trees off an entire country. By 6 9s, we're looking at a 1.5 megaton blast. That's big asteroid impact territory. But things get really weird as we cross the threshold of worlds. At 8 9s, time dilation kicks in so severely that the atmosphere just feels like a thin fog to the needle. It punches right through, totally intact, delivering a 15 megaton impact. Jump to 12 9s and it carves out a 50-kilometer crater with 15,000 megatons of force. Complex life actually survives that, though. You'd feel the earthquakes everywhere. But 17 9s, that's where our Lorentz factor hits 7 billion. The needle strikes with 43,000 megatons of energy. The regional crust melts outright, and the global ocean boils to steam for an entire day. Everything above the microbial level is just gone. Which brings us to the terrible climax of our Earth ladder, 24 9s. Here, the energy hits an incomprehensible 1.5 billion megatons. To put that into perspective, that is 15 times stronger than the asteroid that wiped out the dinosaurs. The Earth's crust doesn't melt at this point. It instantly vaporizes. The mantle liquefies. Our entire planet is converted into a spinning, glowing orange spheroid of magma. No atmosphere, no oceans. But wait, we can push the physics even further. See, the Earth has a gravitational binding energy of 2 × 10 to the 32 joules. That's the exact amount of energy you'd need to blow the planet apart so violently that gravity could never pull the pieces back together. So, how many 9s do we need to completely overcome that binding energy? 29. At 29 9s, there is no Earth left. The needle arrives with the kinetic energy of a small star. The planet doesn't just explode. It instantly expands outward as a massive sphere of plasma. If you were standing on the absolute farthest side of the planet, say down in Patagonia, you would be vaporized into plasma before your optic nerve could even register the flash of the impact. All that's left of our world is a diffuse shell of cooling cosmic dust, expanding outward forever. Section 2. Hitting the sun. Escaping the planetary scale. Having thoroughly unmade the Earth, let's shift our focus. The brilliant theoretical physicist Dr. Lena Aris took this thought experiment to the next logical level, moving from a tiny planet to the heart of our solar system. She was asked an incredibly specific question. How fast would the needle need to travel to blow out the core of the sun so violently that it momentarily turns our star into a giant glowing donut? Well, the answer requires a massive, almost absurd leap in scale. You need 54 9s after the decimal point. Let's look at the terrifying math here. At 54 9s, the Lorentz factor is 10 to the 27th power. The kinetic energy is 10 to the 40 joules. Let that sink in. This tiny needle now carries 1/10,000th of the energy of an entire supernova. From the sun's perspective, the needle's length contracts down to a microscopic quantum dot, literally 1/10,000,000th the size of a single proton. And for the needle itself, time dilates so intensely that the 8-minute journey from Earth's orbit to the sun takes just a fraction of a second. The atoms of the sun literally appear frozen in time. The needle enters the sun's corona, and it doesn't even slow down. The plasma is so thin to it, it might as well be empty space. A tenth of a second later, it hits the incredibly dense solar core and finally smacks into a proton. The collision energy hits 10 to the 36 electron volts per nucleon. That completely shatters the Planck limit. The energy is so impossibly concentrated that standard astrophysics completely breaks down, and the bizarre rules of quantum gravity take the wheel. And the result of that impossible collision? It's not a shower of particles. It instantly rips open a microscopic black hole right in the center of the sun. Look at this stark, terrifying contrast. This new black hole has a diameter of just 16 centimeters, about the size of a basketball. Yet it packs the massive weight of a small moon, roughly 1% of Earth's total mass, all crammed into that tiny space. Now, deep inside the sun, this basketball-sized black hole doesn't just harmlessly evaporate away through Hawking radiation. No, it starts to eat. It accretes solar matter at a staggering rate of 670 billion kilograms per second. To put that into perspective, it is swallowing the equivalent of a literal mountain every single second. At that rate, its mass doubles every 4.7 years, which means it will completely consume the entire solar core in just a few decades. Section 3, the 1-hour donut, a transient cosmic phenomenon. But remember Dr. Aris's original prompt? It wasn't about a black hole, it was about a donut. We're now arriving at the breathtaking visual climax of our explainer. Let's map out the violent timeline of this fleeting cosmic event. At impact, the black hole forms. Sure, but the needle also dumps its supernova-level kinetic energy right into the core as a massive shockwave. In a tenth of a second, the core temperature spikes to 100 billion Kelvin, creating a hyperlethal fireball of gamma rays. 10 seconds in, radiation pressure blasts the inner layers of the sun outward at relativistic speeds. And then, at exactly 30 minutes, the sun's visible surface erupts. The center has been blown out so violently that for a brief, glorious window, the sun forms a perfect, brilliant, glowing donut. But as Dr. Aris pointed out, gravity ruins everything. Just 1 hour after impact, that beautiful donut starts to collapse. The black hole at the center has grown, and its gravity begins violently ripping the inner edge of the plasma ring back inward. Fast forward exactly 1 day, and the donut is completely gone, replaced by a chaotic, asymmetrical mess, a rapidly infalling ring of turbulent gas churning out blinding X-rays and gamma rays. Which brings us to the chilling resolution for our solar system. Physicists call this a failed supernova. There was no explosion bright enough to actually unbind the outer layers of the star. Over millennia, the black hole will eat the rest of the sun, but the total mass remains exactly one solar mass. Because the gravity hasn't changed, the planets just keep right on orbiting as if nothing happened. Except there's no heat, there's no light. Within weeks, Earth freezes completely solid. Our oceans turn into towering mountains of ice. Anyone looking at our solar system from afar would see nothing but a faint ring of gravitationally lensed starlight, a tiny black hole silhouetted against the Milky Way, just a ghost where our star once burned. To ground this wild journey back into reality, let's return to the physicist who mapped it all out. Dr. Alina Aris reminds us, the needle is gone. It was gone in the first Planck time. It was never really there, just a carrier for a question. It's a haunting observation, right? It reminds us of the immense untethered power of thought experiments. The needle was just a vehicle to push our understanding of physics to its absolute breaking point. We just took a 0.1 gram needle and used it to unbind a planet and completely hollow out a star. It shows us that in the universe, physical mass is entirely secondary to speed, and extreme energy can rewrite the rules of reality in an instant. So as we wrap up this explainer, I'll leave you with a final, provocative thought. Now that you've seen what happens when we push kinetic energy to the absolute limit, what other cosmic rules do you want to bend? Keep wondering, keep questioning, and I'll see you next time.